Hello everyone, welcome back to Calculus. And this time we are moving on to a new section, another kind of application of derivatives. And this time hopefully you will see the connection between limits and the derivatives again. So the application I'm talking about here, it is the topic in section 4.8, L'Hopital rule. Okay, it is the way to use derivative to find out a limit, certainly a special kind of limit. So let's take a quick look the statement of the L'Hopital rule. When we consider the limit, okay, of a quotient, let's say it is f over g, f of x over g of x, and then somewhat if you can figure out the this quotient, it is in the indeterminate form. And we will explain a little more about the indeterminate form using the examples below. Okay. When you figure out, anyway, if you figure out this quotient, it is in one of those indeterminate forms, like 0 over 0 or infinity over infinity, as x approaches to a certain number, or could be this a could be infinity too. And then the L'Hopital rule simplifies the limit of, the limit of such a quotient can be calculated. The limit of the quotient of the derivatives. Okay, I didn't use the word quotient, but anyway, don't get confused or mixed up with the quotient rule. Really, this time we are considering the limit in a quotient form, and it is in the indeterminate form, and then the limit can be found by taking the derivative of the numerator and taking the derivative of the denominator. This is the L'Hopital rule. So let's take a look. These are the examples I just took directly from the textbook, and hopefully it may be easier to follow. And keep in mind there are two indeterminate forms, 0 divided by 0 or infinity divided by infinity. Okay. So the first example, actually it has part A, B, C, D. We are considering situation 0 over 0, 0 over 0. Okay, so in this case, the limit we are considering as x approaching to 0, it is 1 minus cosine x over x. And you want to know some basic signs and the cosines. Actually, I put a little material right here. Sine 0 certainly to 0. Cosine 0 is 1. So for part A, at least for now, we need to use the result of cosine 0, which is 1. So 1 minus 1, it is 0, right? Denominator is 0. So this is exactly the case we said in the form of indeterminate form, 0 over 0. Okay, but clearly it's not necessarily 1. It could be of anything. That is the reason we want to call this as indeterminate form. And then how do we know the answer? We use the L'Hopital rule. We take the derivative of the numerator and the derivative of the denominator. Derivative is constant tends to be 0. Derivative cosine tends to be negative sine x. Okay, cosine itself, it is preceded with this minus sign. So I'm having minus negative sine x. And then remember to find our limit, we always plug in value. Actually, we did this in the very beginning because it's not doable. So with the L'Hopital rule this time. And then we figured out we want to give a try to plug in value or the direct substitution to find the limit again. And it works very well. Sine x. This time we replace x with 0. It is just sine 0. Sine 0, as we reviewed a moment ago, sine 0, it is 0. Sine 0 is 0. Cosine 0, it is 1. Okay. So in this case, we figured out the indeterminate form 0 over 0, it is 0. And also, I really want to mention another very important example, another very important limit here. Okay, what would happen if we consider limit of sine x over x as x approaching to 0? This is in the indeterminate form, right? Sine 0 is 0, 0 x is 0. So it is in the form of 0 over 0. Now, according to the L'Hopital rule, we take the derivative of the numerator, derivative denominator. So the limit it is just cosine x as x approaching to 0. Or simply it is cosine 0. Or really it is 1. I really believe in the very beginning of the semester, I did present this limit when we introduced the concept of limits. So this is a limit that you want to keep in mind all the time. And from time to time, we do use this limit a lot, sine x over x, okay? And there's another limit, and we will see the other important limit when we get there. Let's just finish this example, 4.38. The limit in the fashion of 0 over 0. The second one, limit as x approaching to 1 sine pi x and log n of x. And we still have to deal with sine pi, right? If we consider direct substitution. Sine pi actually it is still 0. Sine pi it is 0, okay. And then also there's a logarithm. Log n of 1, I want you to know, if you are not familiar, and you want to, from now, you know this thing very well, log n of 1 it's 0. Log n of 1, 0. So indeed, I'm saying for part B, it does fit the situation perfectly, 0 over 0. And then we use the L'Hopital rule. We take the derivative of the numerator, and which involved with the chain rule, right? So I got the extra pi in the front, okay. Certainly sine tends to be cosine. Derivative of denominator, which is just 1 over x. And still keep in mind, to find out the limit, the first choice, it is always direct substitution. And I did consider in the beginning, and I figured out it's in the form of 0 over 0. And then use the L'Hopital rule, I get to this point, and give a consideration, give another round try of direct substitution. Pi times cosine pi. There's nothing wrong with that, right? Denominator, that's 1 over 1. And cosine pi, remember those basic signs and the cosine. Do I have cosine here? Cosine pi, yeah, I do have cosine pi, which is negative 1. So this time, what we figured out here is such a limit, it is negative pi. It is negative pi, okay. And how about it? Let's take a look, quick look what so far we got. We're talking about the limit in the indeterminate form, 0 over 0. We said actually we figured out it could be 0, it could be 1, it could be negative pi. Now I hope it makes more sense to say 0 over 0, it is in the indeterminate form. And it could be of anything, like 0, like 1, like negative pi, okay. So let's continue working a little more about the indeterminate form. And as x approaching to infinity, well, I hope you see 1 over x, it is approaching to 0, right? And also we do have 1 over x in the numerator part, which is 0. But e to the 0 is 1. So overall, together, numerator, it is 1 minus 1, it's 0. Denominator is 0. So believe it or not, this is still the case. We are having the indeterminate form, 0 over 0. I apply the L'Hopital rule. I take the derivative of the numerator. Numerator is 1 over x, so it should be considered as x to the negative 1 using the power rule. Just I got a derivative for 1 over x. Then derivative of this is derivative denominator. For the numerator, somewhat a little more complicated. It does involve with the chain rule and the rule for the exponential function, e to the 1 over x. Remember, in general, the derivative of exponential function, we always have the same exponential term back, and then we need to calculate the derivative of the exponent, the power. The exponent, it is the power. So derivative 1 over x, and which is really the same as the derivative of 1 over x in the denominator we did a moment ago. So it's the same. And this -1 part, I hope you see, maybe, I'm not sure, just make sure. I didn't consider -1. I didn't take the derivative numerator. But anyway, the derivative of -1, it is just 0. So I'm saying this -1 times x to the -2 is cancelled. The limit we are considering, really, it is in the fashion of e to the 1 over x as x approaching to infinity. And again, 1 over x, it is approaching to 0. So e to the 0, it is 1. And this time, we are having the limit as 1 again. Okay. One more case for 0 over 0. X approaching to 0, sine x. We did a few rounds of sine, right? And sine and the cosine. Sine x again, which is 0. -0 is 0. 0 squared is 0. So I'm saying from direct substitution, I observed this limit. It is in the fashion of 0 over 0. Okay. And then using the L'Hopital rule, and I calculated the derivative of the numerator. Some cosine x, x is -1. Cosine x -1 over 2x. And then if we plug in value as x approaching to 0 again, okay, denominator is 0. Then the numerator part, we are having cosine 0. Cosine 0, remember, it is 1. So 1 minus 1 is 0. So part D, I really want to say, when you calculate a limit, you feel you needed to use the L'Hopital rule. Indeed, it could have been used once, and it could have been used twice, or even more. As long as you are sure the limit, it is in the indeterminate form, 0 over 0. You can keep on using the same rule again and again, that's what I'm saying. So at this moment, I'm taking the derivative of the numerator. Cosine x tends to be negative sine x, and the derivative is -1 tends to be 0, -0 here. Derivative denominator, which is just 2. Okay, I use the L'Hopital rule 2 times. I reached to this point, and then I figured out this time it works just fine to use the direct substitution for direct substitution. So I replaced x with 0, which is sine 0, which is 0. -0, still 0. So overall, the limit, it is just 0. So this part, we are talking about section 4.8, L'Hopital rule. And it can be used to find out some special limits in the indeterminate form of 0 over 0 or infinity over infinity. Thank you for watching. I'll see you next time.